Okay, let's just dive right into this. Welcome back to The Explainer. Today, we're tackling what is genuinely one of the most fascinating engineering challenges in all of modern technology. We're looking at how databases scale way beyond the physical limits of a single machine. Seriously, we're going to look under the hood of the internet's biggest systems to see exactly how they manage, well, basically impossible amounts of data.
To really put this into perspective, think about Instagram for a second. Instagram stores over 100 billion photos. Let that sink in. There is absolutely no single server on Earth, I don't care how incredibly powerful or wildly expensive or highly optimized it is, that could hold that much data or handle that kind of traffic alone. It is literally physically impossible. So what do?
How does a system actually scale beyond just one machine? Well, I promise you, by the end of this explainer, you are going to understand exactly how engineers split massive data sets to make this impossible scale a reality. You're going to learn the strategies, the big trade-offs, and the hidden mechanics of systems operating at a true planetary level.
So here's our roadmap for today. We've got concept clarification, range-based partitioning, hash-based partitioning, and consistent hashing. Then we'll hit the hardest problems and finally wrap up with keys and a series recap.
Starting right off with Section 1, Concept Clarification, Partitioning versus Sharding versus Replication. Let's get into it. You hear these terms used interchangeably all the time in the industry, but they are actually very distinct concepts. Let's clear this up using a library analogy. Now, if you remember back in episode 5 of this explainer series, we covered replication. Replication is basically like photocopying an entire library and putting exact copies of that same library in different cities. So every single city has the whole collection. Great for availability, right? But it doesn't solve our massive storage problem. Partitioning and sharding, on the other hand, are about splitting things up. It's like taking one massive library and distributing it across different cities. The fiction books go to city A, the science books go to city B, and the history books go to city C. No single city has everything, but together they make up the whole collection. And when this partitioning happens across multiple independent database servers, that is what we call sharding.
Moving on to Section 2, range-based partitioning, the simplest strategy and its fatal flaw.
So this is the most intuitive way to split data up. Range-based partitioning is exactly what it sounds like. You split data across servers based on specific ranges of a key. Think of it literally like splitting a massive phone book alphabetically across several filing cabinets. Names A through F, they go in cabinet 1. G through M go in cabinet 2, and N through Z go in cabinet 3. And, this is absolutely brilliant for range queries. If you need to find everyone whose last name starts with a B, you only have to open up cabinet 1. You completely ignore the rest of the database. But what's really interesting about this is what happens when real-world data isn't perfectly even.
And that brings us to the fatal flaw, the hotspot problem. Let's say instead of names, you partition your database by date. Seems super logical, right? But think about the actual traffic. All of today's new user signups, or new messages, or new photos, they're all going to hit your single newest shard. That one specific server gets completely crushed by traffic, while the older shards holding data from, say, 3 years ago sit completely idle. They're just gathering dust. The whole point of sharding is to distribute the load, and range partitioning can accidentally funnel all that load right onto one single machine.
So engineers obviously needed a better way. This leads us right into Section 3, hash-based partitioning, solving the hotspot problem with pseudo-randomness. Instead of using alphabetical ranges or dates, hash-based partitioning runs your data's key, like a user ID, for instance, through a mathematical hash function. You can really think of this like assigning every single piece of data a totally pseudo-random raffle ticket number. And then you file the data based on that random ticket number rather than its actual value. Because those raffle tickets are essentially random, your data gets distributed uniformly and perfectly evenly across all your available filing cabinets. The hotspot problem, solved. No single cabinet gets crushed. But, and there's always a but in system design, right? There's a major trade-off. The pro here is obviously that excellent even distribution of data and traffic. But the con? Terrible range queries. Remember how easy it was to find all the B names in those alphabetical cabinets? Well, in this system, related values are started completely randomly. So if you want to find all users you signed up this month, you literally have to check every single filing cabinet because their raffle tickets put them everywhere. Quick side note here, if this is the kind of content you want more of, subscribing takes just 1 second and it genuinely helps the channel grow. Okay, Section 4, consistent hashing, the industry standard for cloud databases. Let's get into how the big players do it. So, standard hash-based partitioning actually has a critical flaw of its own. When your database grows and you need to add a new server, the simple math changes for every single raffle ticket. You'd have to move almost all your data to new cabinets just to add one server. Absolute nightmare. Enter consistent hashing, used by Amazon DynamoDB, Apache Cassandra, Discord, you name it. And this brilliantly illustrates how they solve it, the round dinner table analogy. Imagine your servers and your data are guests seated around a large circular dinner table, rather than in straight numbered rows. If you add a new chair or if a guest suddenly leaves the table, only their immediate neighbors need to shift slightly to cover the gap. Everyone else at the dinner table, they stay exactly where they are. This means when you add or remove a server in a massively scaled system, you'll only have to move a tiny fraction of the data between neighboring shards. It completely saves the system from a catastrophic reshuffle.
Next up, Section 5, the hardest problems, cross-shard queries and rebalancing. Because look, even with consistent hashing, running a system at this scale isn't magic.
The first major headache is cross-shard queries, what engineers often call the scatter-gather problem. When related data lives on different independent servers, joining that data together is incredibly painful. It's like trying to find out the total number of books across all city libraries. You can't just query one central database. The application itself has to call up every single city library, wait for all of them to pick up, wait for them to respond, and then do the exhausting heavy lifting of adding up those totals manually. It just radically slows down complex queries. And then there's the second headache, rebalancing. Over time, shards just become uneven as data naturally grows or shrinks, and you have to move data around to restore the balance. This is exactly like trying to renovate an apartment building while people are still actively living inside it. It's this incredibly delicate zero downtime operation. You're moving furniture, tearing down walls, all without ever leaving a resident without a place to sit, even for a single millisecond. Mess up a rebalance and data gets lost, or your whole system goes offline. Let's look at Section 6, Keys and Series Recap. How do you actually avoid those headaches? Well, the crucial point is choosing your shard key, because it is literally the most consequential decision you will make in distributed system design. A great shard key keeps related data together without creating those nasty hotspots. For example, say you're building a multi-tenant software as a service app, like a project management tool for different companies. The ideal shard key there is almost always the tenant ID or customer ID. By choosing that key, you guarantee that an entire company's data stays bundled together on one single shard. And since 99% of their queries are just looking for their own data, the query only has to hit one shard. You completely avoid that scatter-gather nightmare we just talked about. Okay, let's take a look at this comparison table to recap the whole problem-solution trade-off journey we just went on. Range-based partitioning? It gives you those excellent range queries, but poor distribution because of those fatal hotspots. Simple hash-based partitioning? You get excellent even distribution, but terrible range queries and a massively high rebalance cost when you try to scale up. And finally, consistent hashing. It gives you that excellent distribution, keeps the poor range queries, but brilliantly lowers that rebalance cost down to almost nothing, which is exactly why it's the absolute industry standard for these massive dynamic cloud databases.
And with that, we've officially conquered sharding. I genuinely want to take a second here to celebrate because this is actually the second to last explainer in our entire database internals arc. Just look at the foundational concepts you've mastered. We started way down at the raw disk level with pages and write-ahead logs. We secured our data with ACID transactions. We optimized it with query execution and indexing. And now we've scaled it across the globe using You now understand the hidden mechanics behind companies like Instagram, Amazon, and Discord. You know exactly how they take impossible data bottlenecks and turn them into smooth, infinitely scalable infrastructure. So my final question for you before our grand finale next time is this. Now that you hold the actual blueprints to massive scale, what impossible system are you going to design next? Keep exploring, and I'll see you in the final explainer.